Hi everyone, so this is a review for Chapter 8 Revision Quiz, Set 1. Well, there's a lot of responses for this one, okay? There's 54 responses, very happy about it. But if there's 70, that's even better. So we will discuss 8 questions for this set, which is question 2, 3, 9, 10, 11, 13, 14, 15. Well, 8 questions. Yes, these 8 questions. Okay, so let's move on to question number 2. Okay, question number 2 shows a diagram. Then this diagram has 3 spring balances. Okay, 3 string balances. So this is one balance, second balance, the third balance. Okay, which are connected to a center that we call as O. Okay, so this we call it as O. Then 3 coplanar forces X, Y, Z are applied to the balance to produce an equilibrium. Okay, coplanar here, what does it mean by co means the same, planar means plane. Okay, means by this X, Y, Z happens on the same plane. You can imagine this X, Y, these 3 spring balances being installed on the table. So they are all on the table, so all the forces are parallel to the surface of the table. So the plane will be the table surface. Okay, you can think of it like that. So this X, Y, Z here are in equilibrium. So they ask you to find what are the impossible force combination for X, Y, and Z. What is impossible? Okay, let me highlight it's not possible. Okay, so let's zoom out and look at the question. Okay, so this is the diagram. So what is this diagram asking for is they're asking for which combination is impossible. So what should we do is we should figure out what does it mean by impossible. Okay, we say this thing is in equilibrium. Okay, it's in equilibrium. So what should you think of when you say equilibrium is the sum of fx should be equals to 0 and the sum of fy should be equals to 0. So in that case, you probably see that, okay, let me label the diagram, make everything clear first. Let's put an axis over here. Then we call this theta. Then we call this alpha. Okay, that will make things a bit easier for us to resolve. So for the x-axis, we will see that negative x cos theta plus y cos phi will be equals to 0. So in that case, we can say that x cos theta is equals to y cos phi. Well, that's a result, but it's not really relevant because this is a relationship between x and y. We still don't know how to relate it to z. Okay, to actually relate it to z, you have to do things in the y component because z only exists in the y component. There's no x component for z. So let's continue. So you know that x sine theta, which is this part up here, okay, this will be x sine theta, and also you have y sine phi. Both of them will be pointing upwards. You resolve the force, so both of them will have forces pointing upwards. Okay, so plus y sine phi minus z equals to 0. So x sine theta pointing upwards, y sine phi pointing upwards. So we treat the upward as positive for this case, minus the downward. Downward is z. Okay, you have to think of this is a spring balance, so the forces, all the forces must be pointing outwards. Okay, we are talking about this point over here, all the forces must be pointing outwards. Okay, so this is the relationship. So now what should we do? Okay, we should move things around to see whether we can obtain some kind of relationship or not. Okay, now we see if we put x sine theta plus y sine phi and we equate it with z, now here you might be able to think of something. Okay, we know that sine here we have the range of between 0, or not 0, is negative 1 and 1. Whereas this y sine phi, the sine phi here will also have a range of negative 1 to 1. Okay, so if this is the case, you will see that x and y will have to be greater than z actually. Okay, from here we can make an inference that x plus y must be greater than z, or else this equation can't be built. Because if x plus y is less than z already, then if you multiply this sine theta, you multiply this sine phi, the number will be even more smaller because the maximum is 1. Means by the maximum is x. You can only go smaller than x. So if something smaller than x plus something smaller than y, if this thing is not exist, if x plus y itself is less than z, then something less than x plus something less than y will definitely be less than z. So this equation will not be valid in that case. Okay, let me repeat my statement. If x plus y is, if x, let me think carefully. If x, we need x plus y, we need x plus y to be greater than z. Because x, if x plus y is equal to z, if x plus y is equal to z, if it's equal to z, then x sine theta, which will make this value even smaller than x, plus y sine phi, which will make this value even smaller than y. Then if you add something smaller than x and add something smaller than y, definitely it will not be equals to z. It will be smaller than z. So you cannot have x plus y equals to z. You cannot have x plus y smaller than z. Therefore, your x plus y must be greater than z. Okay, if x plus y must be greater than z, knowing this relationship here, we will be able to find out that A is our answer. A will be our answer. Because 2 plus 4 is equals to 6 and 6 is less than 7. Okay, therefore this will be our answer. Okay, another way of thinking about it is if you shift this spring balance to be vertical, you change the spring balance to be vertical, something like this, and you change y to be vertical as well, something like this. Then you connect to the same dot, and you connect to z. Then for here, for sure you know if it's in equilibrium, then x plus y must be equal to z. But now if you are going sang it to one side, if you are going sang it here, for sure you need to have a longer x here, only you are able to resolve to get the x that you want. Okay, this one should be longer. That's why the x here must be longer than here, and the y need to be longer. So therefore x plus y must be greater than z. Okay, you need to imagine a bit to think about it. It's really difficult to explain. Okay, but it's about resolution of forces. If you still don't understand, you can ask me, but I hope you understand. Okay, next question. Question number 3. The diagram below. Question number 3. Okay, wait. Okay, question number 3. The diagram below shows two bodies of masses MP and MQ. Okay, you have two bodies of masses, which is MP and MQ, and it's attached to the NP and Q of a light rigid rod. Okay, let's refer to the diagram here. So you have mass P and mass Q, and mass P is attached to point P, mass Q is attached at point Q, and this bar over here, they say it's a light rigid rod. You see the word light in your chapter 8. The light here actually means the mass of the rod will be equals to 0, or we can think the mass of the rod is negligible. Okay, that's the idea of light rigid rod. So the rod is rotated about a vertical axis through the center O of the rod. It means by, okay, this diagram didn't really draw it well. It means by if you have something like this, you can think of this as a plane. Then you can think of this as your axis. This is your axis of rotation. Then you will see there's a rod on top of a table, let's see. Then this is point P, then this is point Q. And here you have mass MP, and here you have mass MQ. And both of them, because this rod is a rigid rod, means by when P rotate this way, Q will also rotate that way. So both of them will be rotating like a circle. Something like this. Okay, well, my drawing is even worse. Okay, but I hope you get the idea. So the light, it's a rigid rod, and when we say it's a rigid rod, then there's an important significance of this keyword. Okay, so now they ask for the ratio of the tension for section PO to the section of QO. So they want to know this tension here. Okay, this, oh no, this color is not clear. They want to know the tension here. The arrow sign shouldn't point this way. The arrow sign should probably point this way. Okay, the tension here, tension of PO ratio to the tension of QO. Okay, they are asking us to compare the ratio between these two tensions. So later we will need to do something called TPO over TQO. And then we want to find what's the ratio behind it. Okay, it's important to know what kind of ratio we need to find. Okay, so let's think. How are we able to get the tension? Well, if you see here, you can see that there's actually two ways of thinking about this thing. One way is thinking about it in terms of chapter 8. You assume this whole PQ thing as a rigid body. So the chapter 8 way of doing things is you assume P, Q, and rod as a rigid body. Okay, so you assume the stick together, the rod together with the two masses as a rigid body. So now you want to spin this thing with the vertical axis through the center, which we call O. Okay, you want to spin it like this. Okay, so let's say you want to increase the rotational speed. You want to speed up the rotation. So to speed up rotation, you need to have an angular acceleration. Okay, you need to have an angular acceleration to speed up the rotation. So how should I find this thing? So let's do it for P first. So the sum of torque of P must E equals to IP alpha P. We are trying to speed up the rotation of P. At the same time, rotation of Q will be sped up as well because this is a rigid rod. Both of them will speed up at the same rate. So we also know that sum of torque at Q will be equals to IQ alpha Q. Okay, now if we think about it, we can probably say that the stick will have to push point P. We'll have to push this mass here this direction. I'm having trouble. You have to push in this direction. This tension here will be perpendicular in order to accelerate. This one will be pushing here. Okay, this tension, this blue color tension here, if we are thinking in the chapter 6 sense, okay, if we are treating it as a uniform circular motion, then we use this tension. But now let's think another way, treating it as chapter 8. So we assume the whole thing is a rigid body. So we are trying to speed up this rigid body. So the rod will push mass P to this direction, whereas for mass Q, the rod will push it to that direction. So you can angular accelerate the whole thing. So to find this thing, how do we elaborate these two equations here? We find the torque first. Okay, the torque will be T of PO times R. Okay, R will be from here to here. Okay, then it's equal to I of P times alpha P. This one will be TQO times R. They are the same distance away from the center. IQ alpha Q. So now one thing you need to notice is, if this rod is rigid, means if I angular accelerate P by that much, Q will be angular accelerated by the same amount. So the angular acceleration for P and the angular acceleration for Q should be equal because they are connected by the same rigid rod. So point P speed up by how much? Point Q, the mass Q will be speed up by that much. So with that said, we can make this even neater by changing this to be TPO over IP equals to alpha over R. Then TQO over IQ will be equals to alpha over R as well. Okay, so now if we equate these two things together, then you get TPO over IP will be equals to TQO over IQ. And since this is a point mass, then the rod is light, the rod is massless, so we can straight away use the equation for moment of inertia for particles. So it will be mass of P R square TQO, then this will be mass of Q R square. So we know that R square can be potong. So if we move things around for the last time, you see that TPO divided by TQO will be equals to MP over MQ. And this is the relationship that we want to find. MP over MQ. So the answer for this question will be MP over MQ. Okay, there's another way of thinking about it. You can think about it in terms of chapter 6. If this mass P is undergoing circular motion and mass Q is undergoing circular motion as well, if both of them are undergoing uniform circular motion, then both of them will have centripetal force pointing towards the center. And we can assume the tension to be the net force pointing towards the center of the circle. So in that case, we can straight write, let's do sum of F towards the center is equals to, this is for P, is equals to MAC P. Then you see this one, we treat it as tension of PO. Then you see it's equals to mass P. Mass P V square over R. Okay, because they are connected by the same rod and they have the same distance from the center, then they will have the same R and the same V square actually. So means by actually TQO will also be MQ, then they will have the same V square over R because they are connected by the same light rigid rod. So means by this one move how fast, this one will move how fast. So the V is the same for both of them and they have the same distance away from the center of the circle, R. So they have the same V square over R. At the end, you will still end up with the equation TPO over TQO equals to MP over MQ. So you still arrive at the same answer. So there's a chapter 6 way and there's a chapter 8 way. And since we are in chapter 8, I discussed with you the chapter 8 way of doing it. Okay, so that's all for question 3. Let's move on to the next question. Okay, question 9. Question 9 shows that you have a uniform disk and this disk has a radius of R and a mass of M and it's mounted onto an axle. Okay, let's use this diagram down here. Okay, so this will be the axle. Okay, and this axle is supported by a frictionless bearing. So you know that when this pulley is turning, when this pulley is rotating, there will be no friction because of the axle. There's no friction due to the axle, okay, because it's a frictionless bearing. So your torque, there will not be torque due to friction. Okay, no frictional torque. And, as shown in the diagram below. Okay, then you have a mass You have a mass hung from a light string wound around the disc, exactly like your experiment. Then mass M is released, which represents its acceleration. Well, it's exactly like your experiment. You should be able to do it, right? But never mind. Let's try it. Okay, so the first thing you do when you face this kind of question is you draw the free body diagram for both of the object, the pulley and the mass M. Okay, let's draw it for the pulley first. For pulley, you represent the object with a circle, center over here. So as you can see here, you have a string coming out from the left hand side, and this string, because of this block here, will be pulled. That's why there's a tension actually. So you can draw there's tension pulling it down. Every force you should label the distance. The distance will be capital R because it has a radius of M. A radius of M pula. Radius of R. Okay. So with that said, we move on to the next free body diagram. Well, there's no frictional torque, so that's the only torque we have. Next thing, the free body diagram for the mass, small m, you have weight of the mass, we call it mg straight away, and you will have the same tension that you see in the pulley just now, because they belong to the same part of the string. So the tension felt by the pulley will be equals to the tension experienced by the mass small m. So this will be our free body diagram. So knowing our free body diagram, we can continue to continue to construct the equation. So for the pulley, we can do a sum of tau equals to I alpha. Okay, before we do that, there's one important thing. Well, this thing will be rotating in this direction, so the angular acceleration will be in this direction, and the small m, this mass will be going downwards. So this will be the acceleration. So if we have determined the direction of the acceleration, it's recommended that you assume the direction of alpha and A to be positive. Okay, you take the direction of alpha and A to be positive. Then your calculation will be easier, I think. Okay, it's much easier that way. Okay, so with that said, so our torque, the only torque will be T times R. And because this torque is going in this direction, that's why it's the same direction as alpha, so it's a positive torque. Then it will be equals to I alpha. I, they tell you it's half mr squared from the question. Then alpha. Okay, half mr squared comes from here. Okay, so that's for pulley. How about for the mass, small m? You have sum of F equals to ma. You take what's along the direction of acceleration minus what's opposite the direction of acceleration. Then it's equals to ma. So at this point, you need to merge these two things together. Only you can find the expression for acceleration, because you want to remove this t over here. You have an unknown t and you have this unknown here. These two are unknown, but you want to find this. Means by you want to remove the tension. So to do that, we cannot combine it yet because this is alpha, whereas this is A. So we have to use a relationship to make this alpha change to become A. We want to make this alpha to become A so that we can do simultaneous equation for these two equations to determine A at the end. Okay, so how do we do that? Recall that for this thing, it's a rigid body, so the acceleration at the circumference here, the linear acceleration at the circumference here will be equals to the radius of the pulley times the angular acceleration of the pulley itself. Well, this is a relationship that you learn from chapter 8.1. Okay, the rotational kinematics. So using that, you can say alpha will be equals to A over R. With that said, you can modify the equation to be half mr square A over R. Okay, so what can we do here is we can remove a few things. The R here and the R can remove, the R here and the R can be removed. So you are left with the equation T equals to half capital M A. Well, this is convenient. Let's shift this around. We want it to be in subject of T. So to be in subject of T, then it will become mg minus ma. Okay, you figure out the maths. Okay, so now we express both of the equation in terms of T, so we can equate these two equations. Equate these two equations, half ma equals to mg minus ma. So we want A as our subject, so we move everything related to A to one side and leave the other things on the other side. You factorize out the A, it becomes half m plus mg. Then you want a common denominator, which you can make it as 2, and this will become m plus 2m. It becomes equals to mg. So now what can you do is you shift everything to the right except for the subject, which is the acceleration. It becomes mass times 2m plus 2mg. Then you will be left with the equation, which is A equals to 2m over m plus 2mg. So based on this, we can say our answer is B. This will be our answer. Okay, it requires some algebraic manipulation, but it's still the same procedure. Build your free body diagram, construct your equation, rearrange your equation so that you can do simultaneous equation, then do simultaneous equation, move around everything, get what you want. Okay? Then you get your answer. Okay, so that's it for question 9. Let's move on. Where are the other pictures? Okay, something's wrong with the software. Okay, question 10. Question 10 says you have a light rod PQ. Okay, this is the light rod, the horizontal light rod. Light rod means by it is massless, and this massless rod is pivoted to the point Q. Okay, it's pivoted to the wall at point Q, so it's pivoted here. Okay, as shown in the diagram. The rod is held in a horizontal position by a string. So this is a string, and because of this string, this rod here remains horizontal. This string basically pulled the rod at this point P here to prevent this rod from falling. Okay, this string is pulling it up from point Q, and it's pivoted at point P, then it's pivoted at point Q. Then you hang a load at the middle of the rod. So now, okay, here's the question. Probably some of you cannot answer it because I write this question, there's a mistake with my wording. It's not if the rod is moved towards P. Okay, if the load is moved towards P. Okay, this load is moved towards P. Which quantity will be decreased? Okay, if this word is changed and you think you are able to solve the question, then take a pause, solve the question. Okay, if no, then let's continue with me. Okay, so for this question, it's actually quite complicated, but drawing a free body diagram might be able to help us out. So draw a free body diagram, we start by drawing the object first. After drawing the object, you figure out the force one by one. First thing, does this rod has mass or not? Well, the answer is no. Okay, you treat as light means by approximate it as massless, or you can think of the mass as being negligible. Okay, so we skip mass. Then the next thing is there any strings connected to it? Yes, there's strings being connected to it at point P. So you have tension at point P. Then the next thing is, do you have any external force? Well, can't see anything. Oh, there's another string. This is also a string as well, but because it's in equilibrium, we can just write it as the weight of the load. So weight of the load come down from here, the weight of the load. Then after that, the next question, any external force? No. Then any contact, any surface in contact? Okay, well, we have something in contact here, and they explicitly mentioned that this is a hinge, so I believe we will have reaction force. So where will the reaction force be pointing towards? Well, this wall is blocking this rod from punching into the right hand side. With this wall, you prevent the rod from going to the right hand side. So to prevent something to go towards the right hand side, the reaction force must be pushing to the left hand side. Okay, then the next thing is this rod logically should be falling. Okay, it should be falling unless it's being pivoted here. If there's no pivot here, this rod will definitely be falling like this. So this pivot prevent it from falling, means by it must exert a force upwards. So there's an upward force and there's a leftward force. So you can think of the reaction force as pointing in this direction. Okay, this is a rough idea of how to determine the reaction force. So this will be your free body diagram, I believe. So that's your free body diagram. So now what they are asking is, if I shift the load towards P, means by Plenty of problem today. If I change this weight of the load here, if I change this weight of the load to be here, if I move it towards P, which quantity will be decreased? Whether it will be the reaction force at Q, or it will be the tension in the string, or it will be this Ry here, the resolve to Ry, this one will be decreased, or this part where you resolve into Rx, this one decrease. So which one is decreasing? That's what the question asking for. So to know that, we have to do something that this is a very fresh question, so you might not have done this before. So what you do is, you know that there's tension, you know there's weight of the load, and there's reaction force. So you pick the point where you don't know a lot of info. There's plenty of information, but you don't have it. You pick those points as the pivot. Okay, because this rod here is in equilibrium, means by you can pick any point as the axis of rotation. You can pick any point here as the pivot. But since we don't know a lot of things here, so let's just pick this point Q here as our pivot. So we say well, it restarts. Let's wait for a while. Okay, so let's pick this point Q here as our pivot. So if we pick this point Q here as our pivot, if we move this weight of the load further away from the pivot, okay, let's write it down slowly. If we move load further away from pivot, what will happen? The torque due to the weight of the load will increase. Okay, because the distance of the weight of the load from the pivot increase. Okay, so if this torque because of the weight of the load increase, it means by the torque that is causing the thing to turn anti-clockwise will increase. Okay, so we have two forces left. Okay, if we treat this as pivot, means I don't need to look at the reaction force, because the reaction force will not cause any torque, because the R is 0 for the reaction force. So you have only two forces left, the tension and the weight of the load. The weight of the load is causing an anti-clockwise torque. It's causing an anti-clockwise torque for the weight of the load, whereas the tension is causing a clockwise. It's causing a clockwise torque for the rod. Okay, so you increase in torque anti-clockwise. If you still want to keep the rod horizontal, what do you need to do? You need to increase the torque for clockwise to balance out the torque anti-clockwise. Okay, so how are you able to increase the torque clockwise? Well, there's only one force that contributes to torque clockwise, means by this tension here will have to increase, because there's no other way. You cannot shift the rope, you cannot shift the string is fixed at P, so you cannot change the R. So the only thing you can change is the T. Okay, so because this thing clockwise is equals to tension times the whole length of the rod, therefore if this thing increase, the tension will be increasing. So tension increases. If tension increases, what will happen is tension in the y direction will also increase. Okay, before this, if this is the original T, now if you make your new tension longer, if you have a greater tension, if now you have greater tension, it means by your Ty will also be greater as well. Okay, that's what I'm trying to say. So Ty increases. So because you know that this thing have to be balanced not just in terms of torque, but in terms of forces as well. So sum of Fy must also be equal to 0. Okay, because it's in equilibrium, sum of Fx must be equal to 0, sum of Fy must be equal to 0, sum of torque must be equal to 0 also. So in that case, what does it mean is, let's look at the free body diagram. What is pointing upwards? Ty is pointing upwards, Ry is pointing upwards, Wl is pointing downwards. We have only 3 things. Okay, Rx is perpendicular, so we don't care. So Ry upwards, Ty upwards, Wl downwards. So you have Ty plus Ry minus W of the load equals to 0. So from here you know that if you increase Ty and you keep the weight of the load constant, because if you don't change the load, to be equals to 0, if you increase Ty, means by you have to decrease Ry. That's why from here we can say that Ry will decrease. And this is the answer that we are looking for after such a long time. This is the answer we are looking for. Ry will decrease. Therefore, the vertical component of the reaction at Q will be decreased. So that will be our answer. Okay, that's question 10. So next question. Question 11. The figure above shows a picture hanging from a string. Which of the following is a graph of tension in the string against angle theta? Well, this one, I will just tell you the answer immediately. The answer is donkey. Why the answer is donkey? You can think of it like this. Okay. I'm slightly exhausted. This whole video is too long already. Okay. This is your frame. Then if your string is like this, then this will be your angle theta, right? Now if you decrease this thing, you decrease this thing, then you have a smaller theta. Then you decrease it even shorter, then you have an even smaller theta. So now imagine, if you want to create 0 degree, means by you want the string to be perfectly horizontal. So if you want to have a perfectly horizontal string, while you are hanging it on a nail, this is your nail, and you want a horizontal string, that means by you have to pull the string to be really tight so that it won't cause a kink like this. Okay, you have to pull the string to be very tight to minimize the triangle that is formed by the string. You have to pull this really tight. You want to pull this really tight, that means the tension will go up. Therefore, if you want the angle to be near 0, you have to put it extremely tight. That's why we will see this approaching infinity thing here. Okay, because if you want the angle to be 0, you have to put it infinitely tight so that the nail won't cause the string to be pulled upwards to form a triangle. Okay, that's the idea here. And when if this angle here is 90 degree, if it's a very big angle, let's drawing pink. If it's a very big angle, then you know that the free body diagram will look something like this. If the angle gets larger and larger, then this thing will move nearer and nearer to the y-axis. So if you move nearer and nearer to the y-axis, then you know that the weight of the picture minus tension 1, don't need to care about equation, but you know that this length of this tension here will get shorter and shorter and shorter if you are approaching the y-axis. That's why the tension will decrease and decrease and decrease and decrease until when it reached angle theta equals to 90, then you see the tension to be equals to WP over 2, because the two tension are pointing upward at 90 degree. Then the only thing downward is the weight of the picture. So the tension 1 and tension 2 will be equals to T. Okay, so that's the idea. So you slowly decrease until when you reach this point, the tension will be equals to WP over 2. Okay, that's the idea behind it. If you got question, ask in the group. Okay, that's all for question 11. Let's move on to the next question. Okay, question 13 here shows a uniform rod. Okay, you have a uniform rod and it's supported at P and Q. So this is the support point, this is another support point. And the support at P and Q are moved. Means by this thing here, this support P and this support Q are actually movable stuff. Okay, you can imagine it like toothpick probably. Looks like a toothpick, right? So you can push this using a force F, and you push here using a force F. Okay, they are the same force. You push it with the force of same magnitude. Then which of the following are true? Okay, you are pushing the thing using forces of equal magnitude. So they ask about which one will slide first. The question always asks about which one slide first. Okay, then they ask about which reaction is larger or which reaction is smaller. So you need to answer these two questions. The first question is which subplot slide first. Then the next question to ask is why. Okay, if you see something whether which support will slide first, you can think it's actually related to Fs max actually. Okay, it's related to Fs max means by if you push with a small f, then the support P and support Q won't move until you reach a certain point where this external force applied is equals to Fs max, only the thing will start to slide, changing from static friction to kinetic friction. So this thing is actually equals to mu Sn. Okay, so Fs max at P will be equals to mu S of Np, and Fs max for Q will be equals to mu S Nq. Okay, what means by what? If you have a higher Fs max, then it will be harder to slide. You need more force to slide. If you have a higher Fs max, you need more force to cause the thing to slide. Okay, so if you know which normal force is larger, then you know which Fs max is larger, whether Fs max is larger at P or at Q. The larger one will be harder to slide, the smaller one will slide first. So that's the thing we are going to determine. We are going to determine the normal P and normal Q. So how do we do that? First thing, well, I can't draw a shape. This is a line. Then you have point P and Q. Okay, so if we want to draw the free body diagram, let's start with, let's say this thing have weight, and we say the weight is around here. The weight of the rod. Then because it's supported at point P and Q, this point P and point Q, they are surface of contact, so you have normal force pointing upwards, supporting this rod here. So you have normal due to P and normal due to Q. So now your task is to find whether normal P is greater or smaller than normal Q. What's the relationship between these two things? So what should you do is, you need to relate it to torque. So you need to know that sum of torque will be equal to 0 because this rod here is in equilibrium. It's not rotating. So if you know sum of torque is equal to 0, so let's try to figure it out. So which point should we pick as our axis of rotation? We should pick the axis of rotation to be a point where we don't know stuff, or to pick a point where we are not interested in the stuff. Okay, so actually we are not really interested with the weight of the rod. We are interested of comparing NP and NQ. We are not interested in the weight of the rod. So actually what we can do is we can pick this point as pivot. If we pick this point as pivot, then we do our sum of torque equals to 0. Then you see that, okay, this is a clockwise thing. Clockwise. This one, if this is a pivot, that means by this will go that way. And this is an anti-clockwise. Okay, so we treat anti-clockwise as positive. So NQ RQ minus MP RP equals to 0. Okay, to be very clear, this will be RQ, this will be RP. Okay, so this is the equation we construct for sum of torque equals to 0. Then from there we can continue to say that NQRQ will be equals to MPRP. Interesting. Okay, so with that said, if we know that from this diagram we can easily see that RQ is greater than RP. RQ is greater than RP. So if we know RQ is greater than RP, then by doing a bit of shifting, NQ and P, then this will be RP over RQ. If you know RQ is greater than RP, then you know that actually NQ will be smaller compared to NP. Okay, you need to do a bit of maths to figure this thing out. Okay, so NQ will be smaller than NP. So if NQ is smaller than NP, from this thing that we said just now, we can say that, oops, messing things up. Okay, from here we can see that Fs max for P will be greater than Fs max for Q. So in that case, this will slide first. Okay, so Q will slide first. So sliding occurs at Q, sliding occurs at Q. This one is wrong. This one simultaneously also wrong. Okay, so we focus on these two things. Then the next thing is reaction at P is greater than Q. reaction and Q is bigger than P. So the reaction here means by normal force, because action reaction, the bar press on the support push back at the bar, so it's a reaction. Okay, so which one is greater? NP is greater. So reaction at P is greater than at Q. That's why your answer, that's why your answer will be A. Okay, so that's it for question 13. Let's move on to the next question. Okay, question 14. Question 14 here says you have a heavy uniform plank. Okay, they purposely mention heavy to let you know that this thing has mass. Okay, and it's having a length of L and supported by force F1 and F2. Well, quite similar to the previous question that we did, but now they specify the position very clearly. F1 is at L over 8 from one end, F2 is at L over 4 from the another end. Well, just look at this picture if you don't understand the words. So now they're asking for the ratio of F1 and F2. So probably what we need to do later will be something like F1 over F2. We probably need to do something like this. Well, before we do anything like that, let's probably draw a free body diagram because it's chapter 8. So this is the bar. Well, it mentions very clearly it's heavy. So I assume there must be a weight of this plank over here, right at the center. Then now we know there's two support, which is F1 and F2. F1 is at L over 8 from one end. So we call this normal 1. And okay, normal 1, we don't use normal 1 probably because they already tell you it's F1, then let's just respect their decision. We call them F1. Then another one, F2, it's slightly nearer to here because it's L over 4. L over 4 is larger, so this will be F2. So this will be our free body diagram. So with that said, we can start to do things now. So again, it's a plank, so probably sum of torque is equal to 0. This should probably pop out in your mind if you are doing it in chapter 8. So where should we put our axis of rotation? Any place on the heavy uniform plank can be our axis of rotation. But we pick the point where we have something we are uninterested in to be the axis of rotation. We are interested in comparing F1 and F2. We are not really interested with the weight of the plank. Therefore, we pick this point here as our axis of rotation. If we put this point as our axis of rotation, let's try to label all the distances from the axis of rotation. So how much is this distance? How much is this distance? Well, you know this distance here is L over 4. Then this distance here, it's half of the plank, so it should be L over 2. From there, you know this will be L over 4. Then you know this is L over 8. And because this is also L over 2, if you take L over 2 minus L over 8, you arrive at 3L over 8. Okay, so these are the important distances for the free body diagram. So let's try to construct the equation. Sum of torque equals 0. So you have two torques here, one caused by F1, the other one caused by F2. If you look over here, you can see that the torque caused by F1 will cause the thing to turn clockwise. I mean, the torque is a clockwise torque. So we treat this torque to be negative. Then for F2, you can see the torque is want to cause an angular acceleration in the anti-clockwise direction. Okay, this torque produced by F2 will be anti-clockwise, so this will be positive. So I usually write the positive first. So F2 times L over 4 minus F1 times 3L over 8 equals to 0. Okay, Now since it's a negative sign in the middle, we can bring things around. F2 L over 4 equals to F1 3L over 8. Well, we want to build an equation which is F1 over F2, so we bring this F2 over to the right hand side. So you have F1 over F2, then the rest you shift also, and this will be 8 over 3L. So now you can do potong, L potong, 4, 8 potong, so you are left with 2 over 3. So 2 over 3 equals F1 over F2. So the ratio of F1 to F2 will be equals to 2.3. So our answer will be this one. Okay, it's more towards a calculation question actually. So that's all for question 14. Let's look at the next question. Okay, question 15 here shows you have a heavy flagpole PQ. Okay, this PQ here is a heavy flagpole, means that it has mass. Okay, and it has weight W. Well, they already label here W, and it's hinged at end P. So this point here is actually a hinge. Okay, then this is a vertical wall. Then it is held in place by a wire from NQ to point R on the wall. So you know from the sentence that this is actually a wire. So if there's any force caused by this wire, it will be a tension. Okay, then yes, they mentioned the tension in the wire is T. Then next, they ask the force exerted by the wall on the end P. Means by they are asking for the reaction force at point P. Where will be the direction for the reaction force at point P? Well, this is an interesting question. Well, you know from our discussion of how to draw free body diagram, if you see this flagpole over here, without this wall, this flagpole will swing into the wall. It will swing into the wall. So the wall is actually preventing the flagpole from swinging to the left. So to prevent something from swinging to the left, you have to exert a force that is going to the right. So that will be our Rx in that direction. Okay, your Rx will be in that direction. At the same time, you know that because of this wall, you prevent this flagpole of this hinge basically. Because of this hinge, this flagpole here doesn't slide down. Okay, it should slide down if there's no hinge at point P. So to prevent something from slide down, you have to push upwards. So your Ry will be in this direction. So if you combine them back together, then the R should be in around this direction. So which of this vector here looks like it's pointing in this direction? Well, SP should, if S is here, P is here, then the direction will be like this. Well, this is exactly the opposite. So SP is wrong. PQ, P is here, Q is here. So if you go like this, this seems to make sense. Then you have P to S. S is somewhere around here, so P to S looks like it makes sense as well. Lastly, P to X. P to X is over here. Well, it shouldn't make sense because you need to have a Y component as well. So this one is wrong, this one is wrong. So we can single out SP and single out SP and you single out PX. So we are left with PQ and PS. Okay, so which one will be the correct one? Well, there's a trick actually for this kind of question. For a rigid body, right, all of the forces must pass through a single point. Now let me demonstrate what does it mean. You see this tension is here right now, right? tension is here, then the weight, if you extend it, it will go something like this. What I mean here is this reaction force at point Q should also pass through a common point as well. So means by this reaction force here will actually also pass through the same point. That means by all the forces acting on the rigid body, if you extend the line in both directions, they will intersect at a common point. Okay, and this common point appears to be S over here. With that said, we can actually deduce our reaction force to be pointing from P to S. That's why our answer will be PS for question 15. Okay, so that's all for question 15. Let's move on to the next question. Oh, there's no next question. Well, that's all. That's all. We have solved 8 questions for Chapter 8 Revision Quiz Set 1. That's all for Set 1. Thank you very much.